Welcome back to the deep dive. You're probably pretty familiar with OLED screens, right? In your phone, your TV, maybe. Super thin, flexible, amazing colors compared to older LEDs. They're already quite efficient, too. But have you ever stopped to think, like, how do they actually make the light? It really boils down to these tiny, energetic things called excitons.
Exactly. And that's really the core challenge for researchers now. Understanding these excitons, controlling them, that's the key to pushing OLED tech even further.
So it's all about the excitons then. And that leads us right into this new work from Kyushu University we're looking at today. Our mission for this deep dive is basically to unpack their breakthrough. It's a new way, a new model to figure out the speed and the kinetics, of how these excitons behave in a special material called TADF.
And this isn't just abstract science. It directly impacts how long your screens last and how bright and efficient they are.
Okay, let's dig in a bit. OLEDs, organic light-emitting diodes. They use organic stuff, compounds to make light. And the magic, as you said, is these excitons. You put energy in, electrons get excited, jump up, and when they fall back down.
Pop. They release that energy as light. We call that fluorescence. But here's the interesting bit. These excitons, they can be in one of two states. A singlet state, we call it S1, or a triplet state, T1.
Okay, S1 and T1.
Right. And the crucial thing, the really important part for us, is that the light, the fluorescence, it only happens when excitons drop down from that singlet, the S1 state.
Okay. So if they're stuck over in that triplet T1 state, they're just sitting there, not making light.
Pretty much. They're effectively dormant, not contributing to the light you actually see on the screen. That's a lot of wasted energy.
Right, a big waste. So how do you fix that? How do you get those lazy triplet excitons to, contribute?
Well, that's where a really big step forward in OLED research came in these materials called TADF, thermally activated delayed fluorescence. It's a bit of a mouthful, I know.
Yeah.
But basically, these materials are designed to sort of lower the energy barrier, the doorway, between the T1 and S1 states.
Like opening a door between them.
Exactly. Makes it much easier for those T1 excitons to flip over, to transition into the S1 state. And once they're in S1,
They can release light, so you get much more fluorescence, much more light overall. Makes sense.
precisely. So understanding that energy gap between S1 and T1, we call it EAST, ΔEst measuring it accurately is absolutely vital.
Vital for, evaluating how good a new OLED material might be.
Yes, and for developing new ones. But here's the rub. Measuring that gap, it has historically been kind of tricky.
How so?
Well, the standard methods often rely on certain assumptions. They could be a bit subjective, maybe not always reliable, depending on the specific material.
Okay, tricky measurements. What about, predicting it with computers? Quantum calculations?
People definitely do that. But quantum calculations, especially for complex molecules, can be computationally very expensive. So researchers often have to make simplifying assumptions there, too.
And assumptions can lead to problems.
They can lead to frustrating gaps between what the theory predicts and what you actually measure in the lab. It slows down the whole process of finding better materials.
Right. Which brings us back to the Kyushu University team. Professor Chihaya Adachi, Research Associate Professor Yuichi Tsuchiya, they tackled this problem.
They did. They developed a new analytical model. It's a way to estimate that crucial energy gap, EAST, more accurately. They did it by using some fundamental physical chemistry principles, and importantly, by properly accounting for how excitons can move between the triplet states themselves, not just between S1 and T1.
So they added more detail to the picture of how these excitons are bouncing around.
In a way, yes. Accurately describing these excited states, it's been a real challenge. This new method they developed is not just a one-off win for the specific materials they tested. It's a tool that can be used much more broadly on other TDF materials, helping clarify these excitant dynamics in lots of future research.
Okay, so it's more foundational.
Absolutely. It contributes across the board, developing better luminescent materials in general, advancing photochemistry. It even opens doors for things like using AI to help predict material properties faster. It's quite significant.
So let's pull it together. The real aha moment here for you listening is realizing how this tiny, almost invisible energy gap, this sort of doorway between two quantum states, singlet and triplet, is fundamentally limiting our screen technology. And this new model from Kyushu University, it gives scientists some much better map, a blueprint for understanding and manipulating that doorway. That means brighter screens, sure, but maybe even totally new kinds of light-emitting materials down the road.
It's a powerful new tool in the toolbox.
So think about that. Just by getting a deeper understanding of these incredibly small, invisible processes, like how excitons dance around, we're unlocking major improvements in the tech we use every single day. Makes you wonder, doesn't it? What other tiny scientific puzzles are out there just waiting to be solved that could completely revolutionize our world next? Keep diving deep.